So this will be about hard probes in isobar collisions and nuclear structures. So this starts from a discussion that Jiang and I had last year at Stony Brook. That's when we realized that there's not too much discussion of using like high PT probes to see whether there's any sensitivity to nuclear structures in isobar collisions. Of course, there are many studies, but not as thorough as all the studies you saw for bulk particle productions. I would try to first talk about hard probes in heavy ion collisions. And essentially, the usefulness of hard probe is that it has a very different scaling with the geometry of the nuclear collisions than the soft particle productions. And then another very interesting stuff is that there are some hard probes, like W and Z bosons, that are sensitive to the isospin dependent quantities. And there are people proposing to use this to probe the neutron spin. We try to make a more realistic projection of what you can expect it at high luminosity LHC. And finally, even your hard probes are not sensitive to isospin, you can still use it to, at current levels, the hard probes are already at the accuracy that you can fine tune your global models. And to have a very good global model description of the production cross section is actually itself a very important question, is like the foundation of all this hard probe studies in heavy ion collisions. So the particle production in heavy ion collisions, we see a lot of about the soft particles, where majority, over 99% particles below 1 GeV are produced through a very different mechanism from hard probes. So in high energy collisions, when you collide things at extremely high energies, you have a very large Lorentz contraction factors. That means that after the collision, the momentum space you see in the Z directions are not coming from the nuclear motions, but from the highly boosted stuff inside the nucleus. So the spatial information of the nucleus are highly compressed, and all you're going to sensitive from particle productions are actually this nuclear density integrated over the Z directions. We call it the thickness function. And whatever your nuclear structure calculations that goes into this eventually gives us a one particle density. Will go, all those information will go into the thickness functions. And besides, this penetration time is very short. That for particle productions, you don't have enough time to talk to the neighbor nucleons. So particle production in these collisions are highly local in the transverse locations. So we hope to use these features to see if there's any connections to the nuclear structure side. So the basics of this discussion is still the Glauber model. So Glauber model from the very beginning is actually a model for calculating nuclear cross sections. It has nothing to do with how many particles are produced, but later we give it more and more content to the details of how we interpret these models, and eventually we come up with different models of producing soft particles and hard particles. So just for the cross sections, you'll start with the thickness function, and in high energy limit, this becomes like more like a probability problem. Is that the cross section for two nucleus to collide is that the probability 1 minus the probability you miss everything, and then integrated over the drag parameters. And if it's for heavy nucleus, this can be approximated by an exponential. So this quantity computes like how much you overlap in densities in the transverse area, and times some specific processes that you want to trigger on. For example, for the total elastic cross sections, this would just be the nuclear inelastic cross sections.
So here I have a question. In fact, can you use the actual wave functions in this TA and TB?
That's some question that I also want to figure out. So right now this is just some one particle densities that when one started with some geometric model, but I think there are also people who try to start from the density matrix. Maybe that's a better starting point to see how the quantum effect that changes this. But I don't have an answer right now how I can change this.
How did you get from the total total nuclear cross section to the specific nuclear cross section of particles type X?
Oh, if this is a real proof, then again this probably picture. Oh, sorry, I'm missing.
Yeah, they're the same signals, right?
Oh, okay. You missed.
Yeah. So if you're interested in the total cross section, then this is actually pretty large for high energy collisions like 70 millibar inside 5 to 7 TeV, and this exponential becomes basically like this for AA collisions that as long as they touch, they will already have a very large probability to interact. On the other hand, if you trigger on some very rare process, this number is much smaller than 1. Now, if you expand this, those rare processes, such as high PT hadron production or weak boson productions, are proportional to the product of this density, the two nuclear thickness functions. And if you figure out a way to use soft particles to select certain impact parameters, you can then use the hard production to study how this product evolve with, for example, impact parameter or centrality. And okay, this is just a recap for the scaling of the bulk hadron productions. So this is the particle spectra you get from the ALICE collaboration, light collisions for all centralities. Below 1 GeV, as most of the particles are, we know that they roughly scales like the number of participants. Goes like this, linearly scaling with the density, the thickness functions. And that's all the information we use to do event classification. And also these particles are prepared from those very small x content of the nucleus. So they don't really care about whether it's a neutron or proton. We evolve it to a high enough scales for gluon productions. So they're isospin insensitive. And of course, this number of binary collisions is going just approximation. For real calculations, more detailed model is that you consider all the final interactions, contribution to the multiplicities. Here you have the nuclear structure input to the thickness, and then there's a model or some physics motivated calculation of how the thickness are mapped to energy deposition at a middle rapidity or at different rapidity. You also need to model what are the level of fluctuation of granularities, not only just at the nucleon level, but this energy you also worry about the fluctuation inside the nucleus and whether there are initial flows in this process. And then there are dynamical models producing more entropies and particles. And there are some hydrodynamic type of response that translates geometry and energy densities into final state momentum space information, including the typical min PT and like elliptic flow, and all of this relies on the transport parameters. And in recent years, people have many collaborations try to fine-tune this whole multi-stage model by comparing to global sets of data in Bayesian analysis. And in general, one finds that for a single system, right now we are still at the level of accuracy of 5 to 10%, depending on which observable you are looking at. And one large hope for this isobar run is that if you take two close enough nucleus, then this uncertainty can be largely cancelled, and then you directly have access to this part. Maybe I should use this online. See. So on the other side of the spectrum, you have the hard particle productions. Of course, the problem is always about the statistics. As you can see, the number drops very quickly. But their usefulness is that for these high PT processes, usually the production mechanisms are very well known to quite good accuracy. For example, in proton-proton collisions, usually for the production of high PT particles, we write down this factorization formula that you start from the parton densities in the nucleus. And there's a hard partonic cross sections that are very well known. And depending on what you want to measure in the final state, whether it's a jet or a hadron, you fold it with the corresponding fragmentation function. And then that gives us a prediction in nuclear-nuclear collisions. And for nuclear collisions, there is a traditional observables that allows you to see what the final state effect does to these high-PD probes. Is the so-called nuclear modification factor. So in the denominator, you try to compare with the particle production in proton-proton collisions, and in the numerators, you compute, you measure the number of particles produced in AA collisions, but of course normalized by the naive multiplicative factors is that how many number of binary collisions a nuclear collision has as compared to a
sorry, very simple. The equation of the spectra is dn over dpt or dn over pt dpt, because it should go to zero.
This is PT.
That's PT
Single without the PT factor. So when you look closely, the spectra actually go down and flow PT.
Oh, okay. So because that's why I was wondering. So here it does go down.
Yeah.
It goes to zero to PT. Okay. Sorry for the interruption.
Yeah, we studied that a couple of days ago.
Because it's a product scale. Sorry.
Oh, it's okay.
I have no idea why they not do the invariant concept.
Okay. And this is just a factor that measures what's your naive expectation if nuclear collisions are just independent superpositions of free nuclear collisions. If that's the case, then this ratio should be just one everything. Or here will cancels with this TAA factor. But in reality, of course, there are very strong final state interactions for these high PD particles in the quark-gluon plasma. They will interact with the partons around them and then lose some energy and also radiate more as compared to the case of the vacuum. And this is actually quite a strong effect. As you can see here, these are the atlas measurement of the nuclear modification factor of jets. And these jets are measured in central to peripheral AA collisions. And you can see even for 1 TeV jets, the yield is only 60% as compared to what the naive expectation. So there are very important final state effects. And of course, these interactions will depend on the path length. But right now, there are not too much of a stress from this high PD community to use this to do like high precision mapping of what are actual geometries and how much details we can really extract. At the current level, people are still trying to, of course, figure out what are the most comprehensive way and correct way to do the calculations. And there are still debates going on of how you treat this process exactly. But I think in the future, one should sort of consider what you learn from jets of more detailed shape and fluctuation of the fire.
So at lower energies, there has been a time when people consider, this kind of model, but also consider fluctuations. Is the fact that if you let's say a neutron goes through and cuts out a tube in the opposite nucleus, the number of neutrons it's going to encounter is not all, not the average, but has some Poissonian-like fluctuations. And then the whole collision would be a different superposition of, these thickness functions than the average. And has this been considered at ultra-relativistic energies?
You mean the local fluctuations?
The fluctuations of in basically this thickness function.
The thickness functions are event by event fluctuating.
Yeah, yes.
So okay, so that's okay. Because, for example, this kind of high momentum value that is reached might be considered like the probability that only one nucleon is encountered, a single nucleon encounters only one single nucleon in front of it, right?
Yes, so maybe this cartoon can be misleading, but
Okay.
in reality, we do have the nuclear position fluctuation, and the produced fireball in the middle will have some hot spots in the trajectory. The problem is that right now the way we do calculation for this energy loss may not be so sensitive
to this kind of fluctuation.
yeah, because you always average over
Okay.
paths on all kinds of orientations. And here is just some of course for this nuclear modification factors, you already average over all orientations and all the transverse locations of productions. So it's not going to be super sensitive to the shape of the fireball. There are observables sensitive to the shape, at least the elliptic deformation of the fireball is the jet VN. So you can not only measure the momentum and entropy for soft particles, you can also do it for hard particles. It comes from a different origin. So at low PT, those V2 comes from that you have a elliptic shaped fireball, and the fireball expands hydrodynamically and then pushes the particles in a cosine 2π modulated way. For jet probes, the origin is different. Is that at some locations you produce a hard process, and then usually at leading order you consider a back-to-back process, two high PT particles. And then if you just focus on one of them, then in some orientations, on average, it transfers a smaller path length. In the long axis, it transfers a longer path length. Of course, it will lose energy to a different amount. Of course, exactly how that energy changes with this path length is another point of debate currently. Here, I just write down what you expected for a very simple model motivated from weakly coupled pictures. So for a parton, in the QGP, you can of course have collision energy loss. It's just some screened Coulomb-like scatterings, and you compute how much energy it loses in the longitudinal directions, and then you integrate it over the entire path until it penetrates through the what you define as the hot QGP region. And then there are also radiative type of energy loss. From these collisions, you can radiate more soft gluons. And actually, it has a different path length dependencies. As you can see, it has one more power of path length over here, and exactly how much of collisional versus radiative energy loss, and how much this jet transport parameters decreases with temperature will give you very complicated path length dependencies. But eventually it will lead to a V2 of these high PT particles. And of course, this is just the energy loss of a single parton. In reality, especially if you want to go to high PTs, usually the experiment with defined jets, which are collimated spray of particles going to these directions, and allows you to also measure V2 at very, very high PT, like a few hundred GeV. And here you can see that you do observe a quite sizable V2 with right now it's already 2% with maybe still 10 to 15% of level of uncertainties in the current measurements. There are other observables people try to think about to make this type of measurement more accurate. Is a recent measurement from Atlas. They call it the leading subleading jet modification ratios. So in this case, you consider not only one jet, but also try to measure the recoil jet. Of course, they will, in most cases, it will travel different lengths. So the jet energy loss of J1, J2 will be different. And you take whatever is the leading jet, compute this modification, divided by the modification of the subleading jet. So on average, the leading jet will be closer to the surface, and this is what you get. So by doing this type of calculation, measurements, the good thing is that you measure jets within the same events, and you take ratio lot of uncertainty cancels, and they can make these measurements cancel a lot of statistics, and I think that the horizontal bars are statistics. Of course, this is still done by a ratio of RAA. So you take the ratio of jet 1 over jet 2, and then further do the ratio of AA over PP. Of course, there will still some residual uncertainties over here, and one can consider maybe this uncertainty level will even be better if you do the isobar ratios for this type of leading sub-leading jets ratios. So the information contained in this is the distribution of the path lengths that you can get in this overlapping area. Of course, I haven't done a further study as to see how sensitive are these to the very small details. But at least experimentalists has demonstrated that this is how they can cancel many of the uncertainties.
Still quite large uncertainty. I mean, the dominating uncertainty is still systematic. Right?
Yes, for central events. For central events, the statistics are quite good. It's just right now they still have plus minus 2.5%. Okay, that's for the colorful probes. There's another class of probes that's also very interesting. It's the colorless probes, including photon and WZ bosons. The nice thing is that they don't interact with the QGP. So in this formula, all of the differences from your expected reference can only come from initial state effect in this case. So the parton distributions in the nucleus. And so this parton distribution in the nucleus, let's call it local parton luminosity. Because if you have the ability to select centrality, then of course this luminosity can change with impact parameters. And if you take one of them, the naive expectation is that the parton I from the nucleus at this specific transverse location is just a superposition of the fraction of protons and proton PDF and the fraction of neutrons and neutron PDF. And the neutron and proton one are fully related by isospin symmetry. But the case is not like the realistic case is not like this. Is that you can have residual dependencies of the nuclear mass number, or to be more specific, the local thickness inside this parton distributions, and people call it the nuclear PDF, which they can extract it from other experiments. So in general, this nuclear PDF also contains of course much weaker than the naive counting of numbers, but still quite sizable dependencies of the local thickness. And this local thickness will further depend on transverse locations. However, if you look at most of the vectorizations people extracted for the nuclear PDF, they make one more assumptions that they only want to extract this function as a function of the mass numbers. So they don't even include the parameter dependencies. It's A dependencies. Of course, this is sufficient if they want to do, for example, DIS and where they don't have the need to define any centralities, and all they need is this average quantities. But for Hebbian collisions, this becomes a more subtle issues. As far as I know, there's only one current extractions from the Finland group. They do this impact parameter dependent extraction of the PDF. In that picture, they have that this modification is stronger in the center of the nucleus, and as you go to the peripheral, the outskirts of the nucleus, this thing, as they parameterize, should go back to a free neutron and free proton. Of course, then you can ask, how does this affect isobar ratios? I mean, of course, if you only parameterize things like this way, they have to cancel in the isobar ratios because they have the same mass number. But the more realistic may not fully cancel as they depend on impact parameters. Oh, that's the Z and that's the W. And for W, you can use it to differentiate UND and therefore neutron protons, which is very useful. As it's sensitive to different distributions of protons and neutrons in the nucleus. So you can compute this production of the W and Z boson productions. The leading out process is just quark anti-quark fusion to a weak boson. At NIOs, you also get some contamination from quark, from gluon splitting the quark, and then fuse with the anti-quark from the other side. But LHC energies, still this NIO corrections are fairly moderate, only like 20%. So you're still very sensitive to the valence structures of the proton and neutrons. And you can do this calculation for proton goes to W plus, which further decays into a lepton plus neutrinos. That's what the experiments usually use to measure W plus in this type of collisions. That's the red curve over here. And then for neutrons is significantly lower, especially in the forward rapidity region. And for proton-neutron, neutron-proton, they are asymmetric, and they're related by the flip in rapidity. And you notice that this process is very rare. It's a few hundred picobar decay into one of the leptonic channel. And on the right-hand side is the one for Z bosons. Of course, Z bosons also coupled to UND differently, but somehow they are not so significant differences to differentiate different types of nuclear collisions. So it's still the W boson in this forward region that contains most of the differences. And now I think even with the current runs from LHC, they already have pretty good accuracies in doing certain stuff in heavy ion collisions. So this is the W plus is in red and W minus is in blue as they measure in light-light collisions and scaled by the number of binary collisions. So it's supposed to be flat if we really know what the model is doing. But of course, it's not flat. And you have a very large uncertainties coming from the determination of this number of binary collisions, because these ratios are always model dependent. You come up with a global model to generate your expectation and then check whether expectation is corrected by measuring this wind productions. But you start to see some deviations, and the level of uncertainties may facilitate some fine-tuning of the global modeling in the future. Similar cases is true also for Z boson productions. And in the past few years, there has been many people start to consider that maybe you can use the fact that W plus and minus sensitive to proton-neutron differences to probe the neutron skin effects. So that's their projections. So here again, you scale the expectation by the number of binary collision scales, and then you introduce the distribution differences of neutron and protons, and you start to see a tiny differences between the shape of W plus and minus at this peripheral collisions. So in the very peripheral collisions, essentially you have slightly more neutron collisions, and that can change the relative yield of W plus and minus. And if you further take the ratio of W plus over W minus over W plus, then if you have a neutron skin, this ratio will start to upband up to a few percent, or 10%, depends on the size of neutron skin you put in light-light collisions. But of course, as you can see, the current level of uncertainty is quite large from the experimental side, and in this estimation, there are additional few percent of nuclear PDF uncertainties over here. And for the nuclear PDF uncertainties, we can probably cancel not all, but maybe a large chunk of them by taking isobar ratios. And for the statistical uncertainties, maybe it's not viable for that experiment, but you can try lighter nucleus where the luminosities are significantly higher.
This uncertainty, I think, is just the
So
neutron
that's the,
skin uncertainty. You're talking about the lines, right?
yeah. So the lines are there. So the middle one is there. I think. Oh, sorry. The black one is what they expected right now, and they vary it by 1 sigma, 2 sigma.
So they're just varying the neutron skin itself.
Yes,
So PDF is not. Probably
it's not
shouldn't,
included.
Yeah, probably it's very small because you're taking a ratio already.
So for this type of ratio, it's the RAA
Yeah.
of W plus and minus is
Right.
not fully cancels, but if you take isobar ratios, it will further cancels.
That uncertainty probably only changes this dotted line, right? Like, you see, you have dotted line,
In the
only
impact
that-
parameter independent picture,
Yeah,
it's just the overall shape.
right.
But if you consider that yes. So the nuclear PDF in principle can also depend on signals. Okay, and we try to do an estimation for what you can expect it of this ratio and also the double ratios in isobar collisions for high luminosity RHC. So we try to couple this weak boson production with nuclear geometric model. For this, we use the Trento initial condition model that I believe there's already a talk about this last week. Just go over some of the essential ingredients. So again, we start from a one particle, like classical density of nucleons that is parameterized in with Saxon form with deformations. And then we also included the minimum distance when you sample nucleons to mimic the short range repulsions. Of course, you can improve this as this model allows you to load like pre-generated like random samples of nuclear configurations. So you don't have always to start from a Saxon nucleus. For example, in past studies, they have asked the nuclear structure people to provide a list of randomly sampled nucleons for helium-3 to generate these initial configurations. I wonder whether this is also possible for heavier nucleus.
It is
Heavier
It's not there. It's actually nucleon configuration for heavy nuclei.
Now, then
do
you
have
just
them?
give me all kinds of samples of.
Do you have them?
For which nucleus?
Be initial, like heavy, those lead to uranium.
We are doing lead simulations right now at leading loiter. So in principle, we can have them.
Like even by even nucleon positions.
Sure.
What does leak mean?
It's a simple interaction. It's not the full entry of chiral interaction.
Okay, the kind of.
Okay, so currently this public version we downloaded just contains beta 2 and beta 4. Of course, for other studies, we also include beta 3 deformation, and we also include that you can have R square terms and denominators. And for this study, we further introduced 2 sets of Saxon parameters so that we can have a proton profile different from the neutron profile, and plus the evaluation of counting different types of boundary collisions. And at this very high energies, it's not just the nucleon profile that becomes, the nuclear profile is important. It's actually, you also need to consider that the proton is not the point. It has a form factor for producing some particles. This is quite important, especially for peripheral collisions. As you can see, most of these differences only show up in peripheral collisions. And at peripheral collisions, whether a proton can produce something or they will miss actually highly depends on your model for the form factor of the PP collisions. And in Trento, currently there are 2 types of proton models implemented. One is just a Gaussian proton, you consider the transverse density is a 2D Gaussian, and then you again apply optical limit of the Glauber model to say that now the probability for the proton to collide is that some internal constituents of the proton may collide. So the collision probability is this 1 minus exponential of some proton-proton opacity times the proton-proton overlapping functions. And then this way you can compute what are the probability for two protons to interact at a certain separation.
This is for constant sigma proton cross section.
Yes, that's constant. But for actual collisions, you have to tune it so that you can always reproduce the PP elastic cross sections.
So for the proton-proton collisions, do you have the same concept of centrality in terms of the multiplicity related to that parameter, or is it different?
Hopefully we can, but the fluctuation is so large that like you produce 30 particles, and then like you have a distribution of particles produced from PP collisions, but a lot of them are just come from dynamical fluctuations. The geometric one is significantly narrower than this. So if you do a cut on this, it's not going to be super correlated with the impact.
And then you're taking into account the fluctuations, but are the hard jets correlated with the central collisions for PP?
That way,
No, I think there's, I mean, the hard collision typically have a more central. I mean, that's they're actually thinking the proton size itself have fluctuation. If you have a high PT events, the proton is actually really also different size because there's I mean, this so-called Atlas use this group of I forgot that they have this global model which consider the proton size fluctuation.
But in that case, the impact parameter is not.
Yeah, they consider the cross-section fluctuation. Actually, they don't consider the impact parameter. Yeah.
Do they correlate the W like WOC boson production with the multiplicity?
Yes, yes. They at least have this Atlas, okay? I mean, it's sort of like linearly correlated, but it's also you put very high
Linearly
multiplicity.
correlated?
Yeah, very high multiplicity. It's also have non-linear behavior. Very high multiplicity because you know the tail can go very. I mean, the soft production might not be the right. It's not a simple geometrical interpretation, right? But typically, it's a linear, right? The more soft particle, you also have the more hard particle. But in the large multiplicity region, there are deviations.
Deviations, it goes faster.
You have more
I
hard than you
think so.
expect?
Yeah, it goes more. Yeah. They did it for JSI. They did also for the Z boson.
Interesting.
Yeah.
Interesting. You can imagine
At least
for
they say so.
jet, but for W, it takes a lot of energy, but doesn't produce any more particles. Is this
There's
still a positive correlation?
it's still hard scattering. When you have a hard scattering, that's well, I don't know the right picture, but maybe the impact parameter there is a bias or whatever. You know, it's not very clear.
What's the picture behind your statement that hard processes come more preferentially for low impact parameter events than larger impact parameter? You made the statement.
Right.
What's
So
behind
this
that?
is my Strickland's this typical picture. You know, there's this.
No, but I can look at that.
So,
It seems almost backwards. Like so, you said you have more hard particles than you would expect if you
No,
just
you
look,
have-
if you just look at the soft.
it will be more central whenever you take.
So
off-
soft
yeah.
scales more with the overlap area than maybe hard scales less strongly with the
Yeah, but
impact
in his
parameter.
picture is that when you produce hard process, is the proton size is smaller somehow. They are closer.
Well, you
The
also
size is different than impact parameter, I guess, right?
I can find.
Then we should probably move on.
And then this way you determine So another one of nuclear model is that you put in substructures. Consider there are 3 hotspots with valence quark, or even more stuff popping nuclear size hotspots. I'm not going to talk about this model. And then you use this interaction probability criteria to stochastically select which pair of nucleons are colliding. And then from this, you can compute the thickness functions. We also assign a fluctuation parameters for every thickness because not every collisions are entirely the same. And especially if you only have one slice of probabilities, there are even more fluctuation just from the kinematic window. Fluctuate the match production in different rapidity regions. And then you convert this because eventually you have to do centralized selections. We have to know how much energy is produced. We use this Trento mean ansatz that convert locally the thickness from the 2 nucleus to the production of viscous transverse energies at each local point. This generalized mean is just this ansatz with a free parameter p to combine the 2 densities. There's actually original motivation for why people do this is that they observe, as we discussed the other day, that in uranium collisions, they find that these tip-tip collisions produce roughly the same number of particles that is side-side. So when one scouts, they originally want to use this generalized mean is because this generalized mean has exactly this property that you can have the same number of participants, but the thickness always scales like homogeneously with T and TB. If you include a hard component, this will not be true.
So here, if you use a quark logarithm, so the in-call will be not the HR production. In high energy, if you use a quark logarithm, not use a binary two component global. So do you expect that difference?
That I don't know, but I think it will introduce some more fluctuations than currently. Okay. But I think for hard process it's okay because the hard process happens at part of black body. Skip this. And use this model, you can start to study like how number of binary collisions and number of participants changes with the variation of the nuclear structure parameters. So on the left is n part, right is n call, taken as a isobar ratios, with the reference nucleus is assumed to be a round nucleus, and you can see if you vary the radius by 2%. Since it doesn't change too much for the n part, as everything happens will happen, so they cannot increase n part by too much. But the number of binary collisions, because it scales as a density square, it can change by a lot, especially for this diffuseness parameters. If you increase some very small density to slightly larger, it will generate a lot more binary collisions than the number of participants. So in general, this binary collision scaling is actually more sensitive to all these variations. And then you can put in the neutron skin. Here we just take a very simple set of parameterizations where you don't differentiate different beta 2 for neutrons and protons. And then you can check that even with or without neutron skins, number of participants, total number of binary collisions, and the Trento energy depositions, they're not sensitive to these effects, at least for the specific 2 sets of parameters. But once you start to differentiate in how many proton-proton collisions, proton-neutron collisions, and neutron-neutron collisions, there are quite sizable differences you can start to observe at peripheral collisions with and without neutron spin. And if you combine this information with the different production cross-section of W plot bosons, you will have some residual effects left over here. And that's what we do. We average different channels by the number of different type of binary collisions to get this W boson production cross sections. And to get some realistic numbers, we also include the decay width of W to these two electron and muon channels, and for Z is the E plus E minus mu plus mu minus channels, and then you integrate it over the resonance peak. It roughly covers that you multiply this formula by about 3 to 4 GeVs and convert to the number of particle productions per unit rapidity. And then you start to consider by taking all kinds of ratios to cancel some uncertainties. The first one is the nuclear PDF uncertainties. That's actually quite sizable. For example, for the W plus, oh, that should be W. For W plus productions, it involves the U collide with D bar. We have 5% uncertainties, and hopefully by taking isobar ratios, this can cancel. And this case is the isobar ratios of W minus and Z bosons. If you take the proton-proton as references, that's all the nuclear PDF uncertainties you can get. And this is isobar ratios, assuming that nuclear PDF only depends on A. Of course, if it depends on impact parameters, right now I don't know how much uncertainties will be left over. But in general, you see a quite sizable cancellation of the PDF uncertainties when you take isobar ratios. And then we figure out 2 ways to vary the neutron skin. There's a very, very rudimentary ways to change neutron skin, but just to see the sensitivities. So one way is just we change the, we start from the same Wilcoxon distribution, but change the diffuseness parameters of proton and neutrons, and we give them this dependence on the symmetry times 0.8 Fermi, roughly corresponding to 0.23 Fermi neutron skin for light 208. Or we can change the radius parameters. In this case, we always change this proportionality constant so that we can reproduce the neutron skin from the first method. And we want to check whether the observables are sensitive to these details.
Some question
Yeah.
here. When we talk about the effects of neutron skin in high-tech collision high energies, so are you just how do you generate the momentum distribution of nucleons corresponding to your density profile of neutron proton? What kind of mechanism do you use to generate the momentum distribution of those nucleons?
So the momentum distributions are often neglected at these high energies because you boosted a nucleon to like 1 TeV.
Okay.
The transverse momentum are usually neglected. For the longitudinal momentum, some of the residual effects are in the PDF. So if you have to integrate everything in nucleon picture, then sometimes the motion of nucleon can be faster than the average motion of nucleons inside nucleus, and sometimes people use Fermi motion to explain what happens to the PDF deviations over here.
This is actually quite a relevant question because people also talk about the initial momentum anisotropy, which are relevant for especially for small system. But for large system, all of those will be quickly washed out if you have any anisotropy. But I don't know if there's a. But the stuff you're talking about is like for short range correlations.
Right. That's what I'm.
Since they are probably important in the beam rapidity.
So you're saying the Fermi is so small compared to the beam and when boost it doesn't matter.
Yeah, because
Okay. Yeah, but you know, at the J Lab, they found that due to solid correlation, the protons are moving faster than neutrons in neutron-rich system. And when you talk about because the solid correlation is proportional to the EMC effect, they also found that in neutron-rich matter, the quarks in protons are modified more compared to neutrons.
in the large X region, very high X region.
High X region, that I don't know. I mean, it's their electron scattering.
Yeah, they always quote the large X, right? It's really large X region where you see this high X region.
maybe.
Close to the.
Yeah, so their conclusion is that the PDF of U parks are modified more compared to the parks.
In the
In
project.
Or is this because you have fewer protons and neutrons? That's
yes,
the reason?
right. You need a neutron proton to make a singlet pair in order to feel the tensor force. That's the cause of the southern correlation. So the quark structure of protons are modified more compared to neutrons in neutron-rich system, and the effect becomes larger and larger when you go to more neutron-rich system.
I think we can write down this as a discussion question, but I don't know. Maybe we need to talk about this.
Okay.
Okay, and then I just pick a few isobar pairs and then see what happens. Of course, for heavy nucleus, one limitation is luminosity, as you can see from future high luminosity LHC projections. So luminosity decreases quite quickly with the mass number. So let's start with the light nucleus system first. And we also want to put on some error bars and the estimation of the time. So we multiply the monthly luminosity. Let's say we somehow convince them to run a whole year for isobar collisions and 6 months for each system. And then multiply the cross sections, and then centrality percentage, the decay width, and then multiply the 2 channels. You can reconstruct the weak boson, and then you use the full rapidity coverage of the detector, and you assume that their trigger is so efficient that everything can be detected, and then you estimate on statistical uncertainties in this way. This is for sulfur and argon for the single ratios. So just take the W plus and minus, take the isobar ratios, and you see that they deviate from. So these lines are the naive binary collision scalings. The Z bosons follows the binary collision scaling quite well. Those ISOSP more sensitive probes are not. But you can take the ratios to further cancel out this overall baseline of the binary collisions because of the differences in the geometry, because we are varying this A parameters to generate neutron skin. And that's what you get for sulfur and argon for 6 months of data with very optimistic estimation. So that's 3 TeV plus 3 TeV. And the coverage is only collecting leptons within 2.5 units of rapidity. Of course, you see that most of the difference is actually not in the middle rapidity, but in the forward rapidity regions. Of course, the detector is not as large as that, but you can try, for example, reduce the beam energy of one of them. So this is what you expect for full coverage rapidity. If your detector can cover up to 4 units of rapidity, then the difference is much larger. So that's where the iso-speed difference is. Or you can try to reduce the energy of one of the beam so that you slightly shift the forward region back to a detector. Of course, in this case, you also decrease in the cross sections. So these two effects roughly compensates, and they roughly have the same error bars. So in this case, the black one is that there's no neutron skin. The green one is the reference value that we put in. And the red and blue ones are varying this reference value of neutron skin by plus or minus 50%. This is for Caulfield. Luminosity is slightly lower, so you have slightly larger error bar. And then we also check that with the same ratios, if you change the reference nuclear Woods-Saxon parameters, for example, you change the A, or instead of changing A, you change R to generate neutron skins. There's a little bit of change, but overall SS flashback their magnitude are almost the same. So this double ratio indeed cancels a lot of theoretical uncertainties to probe neutron skin. Of course,
you introduce the scan difference by just changing the radius.
this is changing the radius. This is changing A.
Yeah. but you change the R in order to produce the same neutron
Yeah,
scan.
yes. And this is for hybrid nucleus, of course, the luminosity is even lower. Right now, you can only differentiate them if you combine all the data points, maybe at 1 sigma level. Of course, this weak process is called weak for a reason. They are very low in yield. You may also consider in the future other probes. For example, if you can measure jet charge and to very high precision and use jet charge at higher PT to correlate with the proton neutrons. This has not been explored, but I think it's still worth trying. Or if you try other like rare processes in UPC events, where to define UPCs, you need hydronic window. But in that case, you have some electromagnetic induced process that depends on the proton distributions. So one, the trigger depends on nuclear matter profile, and the electromagnetic cross-section depends on the protons. Also, Jiang also mentioned that we can project for future circular colliders that will be far outside of the near future, of course. But the luminosity will be a lot more higher, of course.
What's a lot?
So
It's a platonic, I mean, just
of course, it's also
platonic
depends.
luminosity, right? I mean, the rate of producing W3 bosons is quickly increased with beam energy.
Yeah, but is it an order of magnitude? Is it
Yeah.
a factor of 2 or
I think the beam energy is factor of, I don't know, 100 TeV. I think something like that.
100 CV? Yes. But what is the effect on luminosity?
I don't know. It's probably a large number.
Or with that energy, you can just do like fixed target
No, still too low.
with
But it's
that
easy,
you
right?
collect
You
all
just
the forward region.
look the PDF and then change the X and just do a quick. You should do a quick estimate.
Yeah, but if you want to convince anybody to do this, you have to have these numbers.
Yes. I don't know. I didn't do that.
Yeah, and of course, even without this isobar sensitive probes, other hard probes are also very useful. Is that in isobar collisions, you already have these ratios of multiplicities and eccentricity, flow ratios that approximate the eccentricity ratios. Now you can have an independent input for binary collisions. Of course, this is for Z boson productions you have to do at LHC. In that case, if you vary the prior range of your Wood-Saxon parameterizations, then this binary collision actually gives you a lot of sensitivity as compared to particle ratios, and especially for this intermediate centrality regions.
What's the left? It's participants or some kind of linear combination of both, or what? What's the charge?
So the N charge is the Trento formula for the particle reaction.
So it's like Trento entropy or something.
Yes. And now suppose that you can have these are pseudo data, just a demonstration of principle. You have also the number of binary collisions scalings, which are very different from the rest. It's actually independent input to further constrain all these parameters. This is just from Trento studies that this is not even including the multiplicity ratios, just binary collisions plus the flow, the epsilon ratios. You can try to reverse engineer the epsilon, the beta parameters that you put into the pseudo data. Okay, I will just read over the summaries. So the usefulness of hard probes is that first, it has very different scaling from soft particle productions. And second, that some of the probes are very sensitive to isospin. Of course, the minimum limitation of hard probe is the statistics, as you can see in the projection for this W boson double ratios to probe neutron spin. For light nucleus, maybe it's viable if you have enough time at high luminosity RC, but for hybrid nucleus, we need to figure out other ways if you want to go into this direction. And finally, at the very beginning, I also mentioned that the colorful probes, which are not explored too much right now regarding mapping out the exact geometries, you can consider new soft normalized new observables to study passless distributions.
So for the smallest system which had the largest effects because of the luminosity issue, what is the thickness of the neutron skin that you
Let me see.
that you can have there?
Let's see, for this system, I put in 0.8. Yeah, I forgot to put neutron skin number. Yeah, I just have the A number, the variation, the diffuseness. So for sulfur, that's 1620. So that corresponds to vary, this green line corresponds to vary the diffuseness by plus minus 0.1 Fermi. The neutron skin I have to.
I think for calcium is what the measurement from T-Rex is, C-Rex is for 0.2, 0.18.
1.12 or something.
For calcium.
Calcium.
1.2.
Yeah, that's
150, 1.150. The number you put is 0.1 roughly, right?
Yeah, but that's the change in A. There is a conversion from the change in A to the root mean square.
Right. You have that formula in the earlier slide.
So why is it?
But that
So for lead, you said you had 0.2 Fermi or 0.2.
So
So
for
why is
lead,
that
this
bigger?
corresponds to 0.233
So
Fermi.
why is that bigger?
we took it from T-Rex, which is. Yeah. You use
So this was not calculated from the formula n minus c over a.
So 1 minus C over A, the number I put in right now, will give you for P for lead. Neutron skin difference is 6.23. I forgot to put the numbers for calcium, but I think it's even larger. I think it's 2.6.
It would be square, so diffuseness and radius are like squares, so it would be 0.8 squared. So it would be square divided by twice the radius. Or well,
I should just put numbers over here.
I have a different question. We have been hearing a lot of talks about using relativistic high-band collision to probe neutron skin. Can we turn this around, saying that for kind of neutron-rich environment help you to learn something in high-energy physics instead of probing neutron skin? I mean, say we know neutron skin very well. Okay, we know the symmetry energy very well. We have an environment where you have a lot of neutrons, protons. With this asymmetric, neutron-rich environment, help you learn something fundamentally important for you at high energies? Something, something unknown about, say, PDF or, properties of the W boson or Z boson, whatever. Is this a reasonable question?
Yeah, it's just I don't have an immediate response to that. But for neutron-rich matter,
I mean, you have say you have peripheral collision with nuclear with neutron skin. It just give you an environment where a lot more neutron protons, right? Is that help you doing something, learn something important, at high energies?
I wrote it down in the question.
Yes, we are thinking about it. Definitely. Can I go first because it's related to Bauer's point?
I actually have a simpler, even simpler question, not even about the neutron proton difference. In isobar collisions, we have ruthenium, zirconium, and ruthenium is a little bit smaller than zirconium. And I imagined that because the hard probes is very sensitive to the density, and therefore, if you go to very high PT, you should get more high PT production in ruthenium.
Yeah, it's more compact.
Yeah, I asked a student to look into it once using hygiene. It seemed to be very, very small. We couldn't get any difference from hygiene. The statistical error is just too big.
So which are the observed? So is that jet production?
Yeah, or just IPT hadron production.
So this could be more subtle because for jets there are final state effects. The yields becomes higher. The energy loss also. Let's see how it scales with that simple model. So now you slightly decrease the yield, but the density effects.
You have more production, but also more quenching. That's what you're saying.
Yes, because I look at there's the actual isobar ratio for jet production from ruthenium, not jet, a few 5 GeV particle production, hydro productions, preliminary, but I think their results there's almost consistent with one if I take the hydron ratio.
The question is really that how high in PT that you should go to see difference with the statistics.
So I mean the energy loss effect dies quickly with energy, but of course binary collision doesn't go so well. So I would say whenever your RAA is already close to 1, that's the region where you should be able to see the change in binary collisions.
So I want to ask a question. So nuclei are not necessarily well described as far as the interior is concerned with Wood-Saxon. If you have electron scattering, you would have, there's 3, sometimes 4 parameters used to describe the shape, which are seen in the calculations. There are shell effects. So there are wiggles in the density in the interior, which can be different from those of protons. And if you go to light nuclei, you can have cluster substructure, and I think involved in the investigations. So is the Wood-Saxon enough, or at least for the current stage? Because there are other effects than just neutron skin or shape. Or deformation.
But this means you need to provide the configuration which contains this correlation. Right? Because we only have a single one body distribution.
Yeah, but one body distribution, there have been, Alex Brown, for example, did some calculation where he combined shell model with mean field orbitals,
So they can give us some
with some wiggles and some interesting structure inside. So I just wonder, is that a space for you to consider?
Yeah, I think even at the binary collision level, I mean, we have never considered that, for example, beta 2 is not a classical value, right?
Interesting. For example, you use a DFT instead of Wood-Saxon. Do you see a difference?
It's a difference. So so for example, for heavy nuclei, Coulomb causes a dip on the average, a dip in the interior, pushing sort of neutrons to sort of like both,
Oh yeah, that's worse. The
bottom of the bottle shape.
So I have a student who checked this, but only for the soft observers.
Okay.
If you require Wood-Saxon distribution have the same first moment, the second moment, so basically automatically fix the A and R parameter.
Okay.
And that's what the Fujian
Okay.
also did. Then the residual difference are really small for the eccentricity. What happens, the center you have wiggle, but there's only like very few nucleons.
It's a few.
The whole thing is weighted bar square, so the main contribution is coming from the nucleons around the nucleus. Because they are
It can
very
be
small.
because that's the mode where most nucleons are, and then you project it up to two
Yeah,
beams, so
yeah.
they
Yeah.
soft.
Very small impact,
Okay.
the wiggles. But the tail, the difference in the tail, it may predict, yeah. But nobody checked for hard purposes.
No. No, for hard probes, sometimes I think people even use the wrong binary collision profile. So there are certain not at the stage to check.
But I think you showed that the hard probe isobar ratio is actually bigger than the end part ratio, right?
Yes.
I mean,
So those worth checking.
that's,
Further adding more details to the model.
we have time, so people should ask questions.
There's another talk I heard before about this hard process is that they consider this what they call the subthreshold charm production. Is that you try to collide at the 3 GeV like nuclear collisions like a little bit below our production. And then if you nuclear motion accelerates like faster than you can produce the charm even below threshold.
That's part of the FAIR program.
That's right, because you may require like very low heat conditions.
What is the physics you want to get?
Instead of they can the internal motion of the nucleons.
Intrinsic charm.
No.
Okay.
It's just like if some interactions make one nucleon moves faster than all the others.
So that relates to the issue that Bauman raised of the Fermi momentum. I mean, at lower energies, Fermi momentum moves thresholds for particle production, and it's a combination of the Fermi motion and the Lorentz transformation. So I wonder whether, for example, for W's maybe.
Yeah, maybe I read.
No, but the Fermi motion is a few, let's say, a few hundred MeV.
Right.
That's energy independent, right? So
But
it's a
this is
momentum.
not changing. I mean, to order of magnitude, I would say it's a ratio of the momentum to mass. You know, I don't
No.
know without immediately going through. So that's.
But it's a momentum. I mean, the question is how much contribute to the energy.
Right, but you go to another frame, I think it can be of the order of 20%.
In the mean rapidity, or you're talking about
For like changing the energy of the collision, you know, of your nucleon in the row.
yeah, but it only changes your central mass energy by a few hundred MeV, right?
No,
It's a Lorentz invariant quantity. But the moment for me is momentum. It's a momentum, so it's Lorentz invariant. Right?
so
So for me,
in nucleon, I don't remember like the anti-proton production. I think the threshold is 12 GeV at the Wells font. It's 6 GeV or so. You know, that was the discovery of anti-proton. Big change. But it's low energy.
For time production, for instance, you know, the normal size of like 300, if you consider the Fermi motion 50 MeV, that's what the first did.
50 MeV collision, you can produce them, right?
Yes.
Yeah, that's because you adding 300 MeV on the 50 MeV. But if you add the 300 MeV on top of 5 TeV.
But this is Doppler effect.
Yeah.
This is the
No,
Doppler.
but the momentum is a Lorentz invariant, right? If you have px of 300 MeV, that's the same momentum where independent of your beam energy. Let's say you have a momentum in the transverse plane. You boost the system in the beam direction by a huge gamma factor. Your px py doesn't change, right? Your pt doesn't change. I thought this is a Lorentz invariance, right? Yeah, I saw moment.
Yeah, also when we probe the structure with high frequency, has anybody tried to probe the, the bubble configuration or toroid, or like what, changing one and, I don't know, but, yeah. And Wheeler did 40, 50 years ago. Now, if you have two nuclei, really have a bubble inside, toroid or configuration, something. A bubble inside the nucleus. There's nothing there. It's just a vacuum inside in the core.
Somebody should do some calculation.
Yeah, even in recent years, people
Yeah,
Texas and I have been
it's
trying
more,
this.
it's more like.
Oh, I've got another.
Okay.
Okay. Another question for whatever. I mean, do we know whether nucleons are deformed? Let's say proton and neutron, their deformation, some shape. We could.
It's the same as. I mean, through.
Let's say you do the defined two-point correlation function with how big is the shape fluctuation for nucleons?
We ask Jeremy.
I mean, you have this. You mentioned this group of cross.
Yeah.
I think that's not real, right? I mean, they fluctuate when they are closer together. You can get higher.
But there's no experimental evidence for this.
There's what?
There's no other experimental evidence from, let's say, like previous experiments.
You're talking about this color transparency.
No, just the shape
How do-
fluctuation, shape and size fluctuation of the nucleons. I mean, one thing we noticed is in the PP collision at the Large Hadron Collider, the multiplicity you can produce is anywhere from 0 particle to 600 particle. Okay? It's a huge range in the how LHC energy, how many particles you produce in PP collision. Since that's where people have difficulty to actually explain that. That there's a very rare configuration that produces so many particles in PP collision. You have several hundred particles. I mean, what is responsible for that?
I mean, there's a lot of phenomenology there, but there was always a quest for higher energy and considering this phenomenology, dirty physics.
Yeah, right.
But for you, this is the ingredient, right? There's ISR, I think there's a blend of. I mean, I remember reading book, Russian books actually on phenomenology. Elastic processes for hadrons.
I saw Wenbin is going to talk about this, right? Wenbin is coming.
Yeah, he's coming, but he's coming the week 5.
Yeah, but they already do this like
The substructure, but I'm saying this is all in theory, based on diffractive physics. Yeah. Okay, yeah. That probably is the only experimental evidence I have.
I think that's pretty strong evidence because without fluctuation, you miss the cross section by a bit.